This is question 1 from the 2010 paper, and this question is about a substitute for the perfume ingredient ambergris. Ambergris is a metabolic product of the sperm whale and was for many years one of the most valuable ingredients in fine fragrances. Recently, however, it has been replaced with synthetic equivalents such as ambrox, which possesses a powerful amber-type fragrance. This question discusses one possible synthetic route to ambrox, which starts from -driminol, which can be extracted from the bark of the Chilean tree Drimys winteri. In part A of the question, you are asked to calculate the number of moles of ambrox produced per year, given that 10 tons of ambrox are produced in the same time frame. This is a simple conversion of mass into moles, which can be achieved using the equation that moles is equal to mass divided by molar mass. However, when using this equation, we need to be careful with units. The molar mass of a substance is the mass of 1 mole of that substance in grams, and so has the units of grams per mole. Therefore, when using this equation, in order to make sure that our units cancel out appropriately, we need to make sure that the mass of the substance is given in grams. In this question, we're given the mass of ambrox as 10 tons, and so we need to convert a mass of 10 tons into a mass in grams. Now, 1 ton of something is equal to 1,000 kilograms, which in turn is equal to 1,000,000 grams. And so in order to convert a mass in tons into a mass in grams, we need to multiply by a factor of 1,000,000. Finally, before we can use our equation that moles is equal to mass divided by molar mass, we need to know the molar mass of ambrox. The molar mass of a substance is the relative formula mass of that substance in grams and can be calculated knowing the relative molecular formula of ambrox, which is given in the question as C16H28O. Taking the relative atomic masses of the atoms carbon, hydrogen and oxygen from the periodic table at the start of the question, we can calculate the molar mass of ambrox to be 236.384 grams per mole. All that remains now then is to plug our values into our final equation, remembering to convert our mass of ambrox into grams. So our mass, we've got 10 tons, and each ton is equivalent to 1,000,000 grams. The molar mass of ambrox is 236.384 grams per mole, and so if we do that calculation, we can find out that the number of moles is equivalent to 42,304. However, we can't leave that as our final answer. Our starting mass of ambrox is only given to 2 significant figures, 10 tons, and so we can only give our final answer to the same degree of accuracy. And so our final answer to the question of how many moles is in 10 tons of ambrox must be 42,000. In part B of the question, you are asked to look at the synthetic scheme for the conversion of -driminol into the ambrox and give the structures of the intermediates A, B, C, and D. Much of the chemistry involved in synthetic schemes such as these may be new to you, but in many cases it is simply a matter of looking at the functional groups in the molecules and applying chemistry that you do know to slightly different situations. If we do this for our starting material, the -driminol, we can see that it contains a hydroxyl or an alcohol group, which we know to be nucleophilic on the oxygen as a result of the lone pair. Although you may not have seen the reagent, which is called methyl sulfonyl chloride, before, you can see that it contains a chlorine atom, which you will have seen is a good leaving group in nucleophilic substitution reactions. In addition, because the chlorine is so electronegative, it will create a dipole in that sulfur-chlorine bond, which makes the sulfur delta positive and so susceptible to nucleophilic attack. We can therefore imagine a reaction in which the oxygen lone pair attacks the electrophilic sulfur atom to eliminate the chlorine atom as a chloride anion and give the structure of the intermediate A as shown here. Compound A then reacts with potassium cyanide to give you compound B. You will have come across potassium cyanide as a source of the cyanide anion Nc-. If we draw out the Lewis structure of the cyanide anion, we can see that it is nucleophilic on the carbon as a result of the lone pair of electrons which exists on the carbon atom. Looking at the structure of the intermediate compound A, we know that the oxygen is highly electronegative, and so we can see that there is a dipole in that carbon-oxygen bond in which the carbon is left short of electron density and delta positive. And so we can imagine a second nucleophilic substitution reaction occurring in which the cyanide group attacks the carbon, and in this case the leaving group is a sulfonate anion. The sulfonate anion is in fact a very good leaving group because the negative charge placed on that oxygen atom can be stabilized by resonance with the remainder of the structure and the S double bond O's. Carrying out that reaction, we can see that the product from it, the compound B, is the nitrile as shown here. If we look at now the conversion of compound B into C, if we look at the molecular formulae, we can see that the nitrogen atom in compound B is essentially converted into 2 oxygens and a hydrogen in compound C. In this case, really, you just need to recognise that nitriles can be hydrolyzed to carboxylic acids under acidic conditions, with the carbon atom of the nitrile becoming the carbon of the carboxylic acid group. And this takes us through to the structure of compound C being the carboxylic acid shown. Compound C is then converted into the structure in the bottom right hand corner of the mechanism of the reaction scheme there by reaction with the acid catalyst, the para-toluene sulfonic acid. But we don't need to look into that reaction in further detail. What we do need to know is that compound D is formed by the reaction of this intermediate with the reducing agent lithium aluminium hydride. Lithium aluminium hydride can be thought of as a source of hydride or H- ions. Now, the cyclic ester intermediate, if we look at the electronegativity of the atoms involved in that, we will know that that carbonyl group will be delta positive because of the electronegativity of the oxygen atoms. And the carbon atom of carbonyl groups makes esters susceptible to nucleophilic attack by the hydride ion, with the electron density moving up to the oxygen atom as shown here. And this takes us through to a structure for the intermediate in which we've got an oxygen atom which has got extra electron density and the hydrogen atom which we've just added there. Now, tetrahedral intermediates such as these are not stable in molecules where there is a good leaving group attached to the carbonyl carbon atom. And instead what happens is the driving force for the reaction is the reformation of that very strong carbonyl C double bond O. And in this case, we eliminate the leaving group, which here is an oxygen atom. and that takes us through to the intermediate aldehyde, the structure of which is shown there. However, the aldehyde also contains a carbonyl group which has a strong dipole on it, and so in fact aldehydes are more reactive than esters, and aldehyde will react with a second equivalent of the lithium aluminium hydride, with the hydride attacking the delta positive carbonyl group and pushing the electron density up onto the oxygen of the carbonyl group to give us the intermediate structure. Got the oxygen with a negative charge, and then we've got the hydrogen we've just added and the hydrogen we added previously. Now in this case, the tetrahedral intermediate, there isn't a good leaving group on that carbon, and so instead this simply picks up a proton in the acid workup to take us through to the structure of compound D, being the alcohol with the two hydrogens that I'm just going to draw in blue here having been added from the lithium aluminium hydride reducing reagent, and that's the structure of our final intermediate, compound D. Now in reaction schemes such as this, you're not asked for any mechanistic detail. You are simply required to draw out the structures of the intermediates A, B, C and D. But I think you'll agree that by thinking through the mechanisms involved in each of the reactions, it helps to clarify the structures of those intermediates. In part C of the question, you are asked to use the yield of the individual stages to calculate the quantity of tree bark needed for the annual synthesis of 10 tons of ambrox. Part I of the question asks you to calculate the overall percentage yield of ambrox in the synthetic scheme shown. If we look at the first step, in which the minus driminol is converted into compound A, the yield for the reaction is given on the arrow as 90%. When working with percentage yields, we need to remember that we are always discussing the numbers of moles of each compound and not their masses. So in this case, if we've got a percentage yield of 90%, what this means is that if we started off with 1 mole of our minus driminol, we would produce 90% of 1 mole of the compound A, and so we would produce 0.9 moles. And what we've done there is multiplied the number of moles of our starting material by the percentage yield of 90%, or 0.9. This 0.9 moles of compound A is then reacted with potassium cyanide in a 60% conversion, and so we can calculate the number of moles of compound B produced in exactly the same way. We start off with 0.9 moles, and there's a 60% conversion, and so we times by 60%, or 0.6, to find the number of moles of compound B produced to be 0.54. We can work through each of the individual stages in the synthetic scheme to calculate an overall percentage yield for the reaction. So if we do that sum, we've got a 90% yield multiplied by a 60% yield times by an 84% yield, then a 75%, 86%, and then finishing off with an 85% conversion. And if we do that sum, what we find out is that if we started off with 1 mole of minus driminol, we would produce 0.2486 moles of our ambrox, or the percentage yield for the reaction is 24.9%, and that's given to 3 significant figures. In part 2 then, you are asked to use this overall percentage yield to calculate what mass of minus driminol would be needed each year if all of the commercially synthesized ambrox was made using this method. Now the minus driminol reacts to produce the ambrox with an overall yield of 24.9%. That's what we've calculated in part I. Remembering that when discussing percentage yields, we're talking about moles and not masses, we can write then that this 24.9% is equal to the number of moles of ambrox produced divided by the moles of minus driminol, which would be needed as the starting material, times by 100%. Now we need to know the number of moles of ambrox in the 10 tonnes which is produced per year, but we've calculated that in part A of the question, and so we can substitute that value into our equation. So in part A of the question, we calculated that the number of moles in 10 tonnes of ambrox was 42,304. So we can now rearrange that equation and do a relatively simple calculation to find that the number of moles of minus driminol needed to produce the 10 tonnes of ambrox which is produced per year is 170,109. And actually, if we think about that, 24.9% is approximately a quarter, and so we would expect the moles of minus driminol needed to be about 4 times the number of moles of ambrox. The question, however, asks us to calculate a mass of minus driminol, and so the final step of the calculation has to be to convert this number of moles into a mass. We know the molecular formula of the minus driminol to be C15H26O. It's given in the question, and so we can calculate the molar mass of minus driminol to be 222.358 grams per mole. Therefore, we can use the equation that mass is equals to moles times the molar mass to calculate the mass of minus driminol, which is equivalent to the 42,000 moles that is needed. And so substituting these values into our equation, we need 42,304 moles, and each of those moles has got a mass of 222.358 grams per mole. So if we do that sum, we calculate the mass of minus driminol needed to be a massive 37,825,097 grams. But because that number is so big, and because the information is given in the question is given in the units of tonnes, it's better to give our answer in tonnes. So we need to simply convert the number of grams into our tonnes, remembering that 1 tonne is equal to 1,000,000 grams. And so our answer becomes 37.825 tonnes. Again though, we need to give our final answer to the same degree of accuracy as the least accurate number in our calculation. All of these calculations are based on the fact that we need to produce 10 tonnes of ambrox per year, and so we can only give our final answer to 2 significant figures, and so our final answer becomes that we need 38 tonnes of the minus driminol in order to produce the 10 tonnes of ambrox that are produced per year. You'll notice that throughout these calculations we've carried through as accurate a number on our calculator as possible, and then only at the final stage of the calculation converted the answer to the degree of accuracy that we need. In the final part of the question, we're told that the bark of the Drimys winteri tree contains 0.5% by mass of the minus driminol, and we're asked to calculate the mass of bark that would be needed if all of the commercially synthesized ambrox was made using this method. So in part 2, we calculated that the mass of the minus driminol needed was 38 tonnes. Now this 38 tonnes is equivalent to 0.5% of the mass of the tree bark needed. And so we can calculate the mass of tree bark needed by simply working out what 100% would be. So 38 tonnes is equal to 0.5%, so we can divide it by 0.5% and then times by 100% to find out what 100% would be. And if we do that calculation, we come up with an answer of that we would need 7,565 tonnes of tree bark, which again we can only give to two significant figures of 7,600 tonnes. And so you can see that we actually need a very large mass of tree bark in order to produce the amount of ambergris that is needed for these synthetic perfumes.